All right.
Ya que se viste hace rato, esté a cargo de
Yeah, good morning. And now I want to send a link
Vamos a ver acá.
for you to
No,
check
tenemos
the
solamente eso.
electronic materials
Ay,
on
consúltale
the
a
online
Diego,
class.
Ahí vamos
And
para
I
allá.
sent the link
Vamos.
on the chat box. You can search the link and use your email address to join the online class. Then you can check the electronic materials. Okay. And I'm Lydia, and I am a trainer in the Hangzhou Training Center of Huawei. And I'm responsible for these 2 days, these 2 mornings, and introduce 2 topics for you. One is for this one we talk about today, the overview of the communication network development, mobile communications. And the other is about the 5G industry deployment and evolution, which we'll talk about on tomorrow morning. And each morning we have 3 hours, so we divide into 2 parts. The first part we will take about 1.5 hours to introduce the first topic. Okay, here you can see it. There are 3 topics, 3 chapters we want to introduce to you on this morning. And the first part, the first 1.5 hours, we will introduce the architecture evolution and part of the technologies. And the second part, the second class, we will introduce the remaining information. Okay, first for the topic. Yesterday we introduced our trainer already introduced about the fixed communication, right? The fixed communication. So today we'll introduce the mobile communication, and we want to introduce some different parts between the fixed communication and mobile communication. Okay, and after this part, we want you to know these three concepts. One is the basic concepts of the communication networks. Some names, some read, some release about the basic concepts. Second one is the network development. How can we develop the mobile communication network? The components. And the third part is the evolution process from 1G, 2G, 3G, 4G, 5G. And we already improved the both device and the new key technologies. So you need to know the difference key technologies to deploy different RAT. And also for the radio network architecture, we also need already do some changes from 1G to 5G. You need to know what are the difference of the architecture. And the last chapter, we will introduce the typical technologies, because during the evolution, there are some problems need to solve. So we introduce the new key technologies to meet the requirements. You need to master some typical technologies. Okay, the first time we will introduce the first chapter, mobile communication network architecture evolution. Yeah, you can find the mobile cellular network is the new conception. What's the meaning of the cellular network? Okay. We say the public radio communication initially used the regional strong coverage technologies. It's the left picture, right? The left diagram show you the regional coverage technologies. And here we see the black word broadcasting station. What's the meaning of the broadcasting station? Focus on the downlink data transmission, right? The downlink traffic. And at that time, the radio station had rather high transmit power, right? The base station had the high transmit power and required the high-res antenna tower. The high-res antenna tower. And the advantages is the wider signal coverage area. Right? The wide signal coverage area. So even dozens or even hundreds of kilometers of the area, of the coverage area. The typical examples for the broadcasting station we listened to, and maybe the TV programs were received by using the antenna. Right. So for the regional coverage technology, is a point to multi-point, right? Point to multi-point. It is the unidirectional
quedan todo esto
transmission
que tú mencionabas.
technology compared with the
Pero, o sea, la meta es esto,
point to
la
point.
meta que define, aparte en la meta y
So
hacerlo
whereby the
nacional.
Esa meta es
coverage
anual,
can be
mensual, ¿cómo se
expanded
anual.
as long as the power
O
is
sea,
large enough
esa meta también es gracias a
and
las
the
prácticas.
capacity is
Claro,
not
Yo,
limited.
mira,
Right?
Belén, no.
Capacity is
Sí,
not
mensual.
limited if the
Bianca,
power
Bianca, yo, entre Bianca y yo me
is strong enough.
Claro. Sí,
We will
sí,
not
entonces
limit
continúa con su
the system capacity. But we said the uplink
El mío
reception
sí,
is
estamos en
not
84.
considered,
Tenemos,
right? Because the base
pero mira, pues
station
nuestro método 216,
have the
257.
strong power. It can transmit
Eso se demora
more data traffic to the user. But
Pues,
for the
oye,
UE,
explícame, ¿cómo
for
es
the
ese flujo
terminal,
de
the power is
ingeniería, de
limited.
Ah,
So
ya.
here we not
Todo eso,
consider the
a ver,
uplink transmission,
muéstrame ese flujo ya.
only
Primero,
consider the
Primero,
downlink
hay un área que
transmission.
le asigna el proyecto. ¿A qué contratan?
But we said in human-to-human communication,
¿qué contratas
both
tenemos?
downlink transmission
Tenemos como
and
9
uplink
CJ,
reception need to be
Esas
considered.
contratas
For
son
the
los técnicos
downlink
que ejecutan
transmission,
proyectos
that
que
means the
hacen la
system
implementación y
capacity.
también que hacen el
And for
diseño.
the uplink reception,
Siempre se ve un
it is the
proyecto se
uplink
divide
transmit
TI
power of the terminal
y PEX.
of the UE,
Ya.
right? So under this background, the
Es en
mobile cellular
RF
network
como aquí ya
technology
les asignaron la
emerges.
contrata.
So
RF
it's
también ya
the
saben
right
en
part,
dónde va a
the
colocar la
right
antena. Le dan un
diagram,
posible candidato, un
mobile
cuadrado
cellular
de la zona.
network. It
Ahí,
is
ahí.
Donde va a ir
cell-based.
la antena. Ajá.
What is
Ahí te
cell-based?
hacen TCCB.
First, we need to know the concept
Ya.
of
Le
the
dan
cell,
a saques
concept of the cell.
Dan al
The
área SAC, y SAC
original
tiene que hacer las
regional
negociaciones
coverage
para conseguir
area is
ese punto,
divided into
ya sea
multiple
casa,
cells,
lo que
from
sea.
the left
Legal.
part to
Todo,
the right
todo lo
part.
que es legal.
Todo legal,
Una
ya.
vez,
And
y
the
una vez
base
que lo haga,
station is
ya firma
established in the
una
center
torre
of
encima
each
CDP.
cell.
Y esa torre
In this
CDP
way,
hace toda la
each
estructura.
base station
Todo
can
esto donde
only
va con
cover
su
a very
comunicación.
short distance,
Para ello, RF
right?
aquí
And the
asigna
terminal
un
can
protocolo que es como,
communicate with
es
the
como una guía de
nearest
dónde
cell.
van a ir las antenas, para qué dirección van a apuntar,
In
en qué
this
altura van a
case,
estar.
it can
Y con
reduce
eso,
the
con respecto a ese
terminal
colo que hace
transmit
RF,
power.
se construye el
On the left
estructura de la
base
torre.
station, on the
Además de
original
estructura,
coverage
también
technology, when UE located at
ejercicio
the
con
edge of the
energía.
cell,
Pero
maybe
todavía
the
eso sigue en
uplink
fase de
data
diseño, ¿no?
transmission is
No, aquí
limited.
en SAC.
The base
Ahí donde
station
empieza.
cannot
Una vez que
receive the
definen todo eso,
correct
recién pasa
uplink
ingeniería.
messages.
¿Y qué es ingeniería?
But
Ingeniería
on
lo
the
que hace
mobile
es hacer todo
cellular
el patio.
network,
Por ejemplo, yo tengo un
the
sitio acá.
the cell radius
El faren que
is
dijeron los
shorter
RF,
than the
la antena lo quieren poner
regional
acá.
coverage technology.
No, o sea,
In
la
this
antena lo
case, the
quieren poner acá.
terminal
En ingeniería
can
definen
use
cómo
the
sea, dónde te gusta el
small
faren, dónde
transmit
gusta el
power to
cuál
transmit
conviene
the
más, si es acá,
uplink
acá
data,
depende, o si es
transmit
acá,
the
por ejemplo,
uplink
hay
signaling,
una ruta en
uplink
la cual tiene que
information to the
gastar
base station.
cuál cantidad de
Right.
postes
So this way
y
can
también por
reduce
otra
the
pasada,
terminal transmit
dónde la
power
velocidad también,
and
tiene
can
capacidad,
increment
todo eso
the
habla.
terminal,
Sí, que todo,
the
también
smart
coordina
terminal,
todo,
the
transmisión,
smartphone,
con la de Saúl,
right?
coordina todo eso.
Transmisión
And
se incluye.
because we say
Es que ellos ven
the
todo
entire
lo que son
network
los
structure
ustedes ven
is
acceso,
like a cellular,
ellos ven
so
los
such
transportes.
communication
Queremos agarrar
is
una mufa,
referred
ellos
to
nos enseñan
as
los
the
hilos de esta mufa,
cellular communication.
hacen todo eso.
Cellular
Tenemos que hacer
communication.
todo eso
So here we need
y
to know
también
the
ven
conception.
qué
What is
antenas
the
van a usar
regional
para todo.
coverage
Ellos lo que
technology?
hacen
What
es
is a
la orden de
mobile
compra
cellular
y la contratan
network?
a trabajar. Una orden de compra donde está todos los precios. O sea, vas a instalar esa antena, te va a costar
Yeah,
5
let's see some
Vas a
evolution
subir un
from
gabinete,
1G
instalar
to
tiene,
5G.
te
Now
cobran
we are in the
según
5G,
eso te van a hacer. Y todo el tendido en la PEX. Por
5G
ejemplo,
era,
si vas
right?
a tener
But
1 kilómetro de fibra, la fibra
during
todos
the
los seguimos
evolution from 1G to
pero en el
5G,
tamaño de
we
obra lo podemos calcular.
already
Si voy
proposed
a
so
tener por
many
lo menos
different
todo 1
types,
kilómetro,
different
imagínate de
reds.
3.000 soles. Y en todo lo
First,
demás,
from the 1G,
todo ese proceso
here you
hace
can see the
ingeniería.
1G is
La orden de
Ingeniería
compra.
también
analog,
saca el presupuesto del
right?
proyecto.
Exacto.
Is
Ajá,
analog.
ellos
But
lo
from
¿Y dónde
2G
están los
is digital.
postes?
Okay.
Los
From
Ellos lo
2G to
definen.
5G is
Número de
digital, but
postes.
Claro,
before
mira,
2G,
a partir
1G is analog.
ellos
It's
definen
the
todo el
first
número de
difference point.
postes, cuánto vas a tener la fibra, todo
And
es una partida.
the
Ya.
digital
Una
is
vez que definen
after
todo eso,
World
Una
War
vez que ya
II.
definen, cierran,
Sorry,
pasa a Civil
sorry,
Ahí donde
I said
la
the wrong.
contrata SDP, que
After
ya antes
World War
habían
II, the
asignado,
first
y
regional
empiezan a
public
construir todo
mobile
el
phone service was launched.
pero ya está definido en los RPs.
But
Y
it
aquí
is
es donde la
restricted
contrata SDP
by
que te digo,
the related
construye toda la
device,
torre.
restricted
Semanalmente
by
nos
the
mandan así fechas,
technologies.
posiblemente
The
cuando inicia y cuando
mobile
termina. Por no se demora
communication
mucho.
didn't develop
Imagina que
fast.
no una fecha de que termina
Didn't develop fast.
el 10 del
And
próximo mes.
after
10
the
del
Bell
próximo mes.
Lab,
Entonces nosotros
after
como
the
área de
Bell Lab,
implementación,
we
ya está
put
en
forward the
construcción
cell-based
y ya
cellular
tenemos el
mobile
diseño y la
communication
OCE
system
validada, porque
solution,
ese presupuesto que ellos hacen
which realized the
tiene que estar
frequency
validado por
reuse
jefe, por
through the
el
frequency
gerente o el
reuse
subdirector,
and
pero al final
improved the
llega a
system
con el director.
capacity. Then we
Ellos valida y
the mobile communication are applied on a larger
Aquí en
scale,
Singapur, donde ya tenemos nosotros acá,
larger
y
scale.
acá. Recibo
And
nosotros
first we
ya
see the
definimos
analog cellular
y
mobile
diseño.
communication
Lo que
system.
hacemos es
That's
ya implementarlo,
1G.
¿no? Empezar a
1G.
que ellos
There are
tengan
three
fibra,
main modes,
le puso todo
three
el
main routes. One
recorrido.
is
Y además también
AMPS.
ya tienen que
The
ir
full
definiendo
name
los
of
equipos
the
que van a hacer
AMPS, anyone knows that? The full name of the
al área que está al
AMPS?
fondo que piden equipo de energía, de los RF que
You can
tenemos
write in
todas
the
las
chat box.
antenas.
I can give you
Todo
the
eso en
response.
fase de Civil War, ¿no?
Claro, aquí ya lo vamos pidiendo. Ajá. Según
Amplitude
forecastando la fecha
modulation?
que SDP nos da de
You
cuándo
mean the full
va a
name?
estar ya hecha la estructura.
Actually,
Imagínate de ahí
the full
nos
name of the
dice
AMPS is
15 más o
Advanced
menos, que tenemos que ir
Mobile
corriendo,
Phone
pues
System.
no vamos a esperar
Advanced
que ellos
Mobile
terminen
Phone System.
y
It
nosotros
used the
recibimos.
analog
Y
cellular
eso es
system
mucho,
and
o sea, muy poco tiempo.
worked in the 800. Yes, yes, Daniel is right. Advanced Mobile Phone System. It used the analog cellular system and worked in the frequency band is 800.
Que siempre viendo la
Works
fecha.
in
Chamba
the
de arriba está ahí
800
en Civil
megahertz.
War.
Lo que pasa es que él su torre se
And
demora
the AMPS
un mes,
is widely used in the North America, South America, and some around the Pacific. They use the AMPS. And the second one, TACS.
Y ahí también es donde pides
TACS full name
Exacto,
is
ahí
Total
donde
Access
empezamos a pedir
Communication System.
Ahí donde empezamos
The
a pedir
frequency
ustedes,
band they use
RF
is
también.
900
Y una vez
megahertz.
imagínate que
900
la torre
megahertz.
lo termina
And it
de
has
construir.
two
Nos
versions.
dan la
One
torre ya
is
construida. Entonces,
ETACS,
nosotros,
one is
lo que nosotros
NTACS.
tenemos que hacer es tenemos
For
7
the
días para
ETA,
activar el sitio. O sea, activar es poner ya al servicio de la población. Solamente al
ETACS
servicio, no al servicio de Claro.
and
O sea, activar las antenas. Entonces, para eso
NTACS.
necesitamos tus recursos, RF.
ETACS is for the Europe.
Otra ya lo
NTACS is for the Japan. For Japan.
Huawei
And
también
the
aquí
standard
interviene.
is very
Ya
wide
cuando
used
interviene,
in
pa,
the
se pone acá.
UK, wide used in the Japan, in some
Bueno, este
Asian
proceso,
countries.
aquí como te
In
dije,
the Asian
se hace
countries.
la estructura. Cuando ya termina la estructura de SDP, se pasa
Then for the
donde es
NMT,
la instalación de todos los equipos.
for the
O sea, en teoría,
NMT
o sea,
is mainly used
aquí
in the
terminan de
North
construir la
Europe,
torre, y
and
nosotros recién vamos a llevar los equipos, instalarlos.
the full name, you know that,
De nosotros
is
tenemos
Nordic
que ganar
Mobile
el tiempo.
Telephone System.
Ellos por eso nos ponen fecha.
And we
Que
say
en ti-
for
en
the
TI,
first
¿qué se
generation,
hacen?
En TI
first
básicamente se
generation
instalan todos los
1G,
equipos en la torre.
Pero no se
Y
ve
it
instalado ya en la
has
fase anterior.
Claro, es que eso lo
disadvantages. That's
hacemos
why
nosotros.
we want to
En
evolve
teoría debería
from
ser
1G to from the
terminamos
analog
la-
to
o sea,
the
termina
digital.
la torre y
Because
recién nosotros
for the
instalamos.
1G,
Nosotros hacemos a la par mientras que ellos van
they use
construyendo,
the analog
nosotros ponemos
technology.
diferentes
They will
equipos,
result
que
in
para
the
llegar el mismo
poor
día que nos entreguen, el
network
mismo día estamos
security.
instalando. O sea,
Disadvantages
tiempo.
is the poor
Tenemos que estar-
network
Sigue,
security.
sigue.
De ahí ya.
And its
seguimos
capacity
aquí instalando
cannot
los
meet
equipos.
the rapid
Y aquí es
market
difícil,
developed
porque
requirements,
como
especially
utilizamos
now
equipos,
to today, to
energizan
5G.
los equipos.
So many
Aquí
people
la
want to
fecha
search
está
the
en
internet,
fibra.
want to
Desde ahí iniciamos el
see,
Civil War
view the
cuando
videos,
está
want to upload,
aquí por lo menos
have the
lleva
live
bastante
data
tiempo.
stream, right? So in this case, it cannot meet the rapid market development requirements, and the terminal are very large, terminal very heavy. So it's gradually replaced by the digital cellular mobile communication. That's 2G. That's 2G. The 2G first one is the GSM, right? The GSM. The full name of the GSM is
Pero
Global System for Mobile
Datafield,
Communication.
ustedes lo piden
Global
después de que
system.
la torre ya esté construida, ¿no?
And it is the
Bueno,
digital mobile
cuando ya esté construida,
communication
sí.
standards
Cuando está
developed by the
Sí,
EDSI.
básicamente cuando está construido.
Porque
EDSI
el
is
mío
just
es,
the
pues, me da cuenta que el mío es
Standard
puro lógico,
Institute
puro
Claro.
Standard
para poner el
Institute.
servicio de la comunidad. como
And
dije.
used the TDMA
Hay momentos que llegamos
technology.
a fin de semana
Okay,
y
use the
digamos,
TDMA.
nos
This one.
saltamos algunas fases.
GSM,
Eso
the
lleva a terminar.
technology.
Una vez que
Sorry,
está TI, lo
is
mandamos a
the
activar y se pone aquí. Esta estación va a seguir
TDMA.
funcionando.
Chévere.
Pero
Do you know what's the
aún
meaning
no
of
conseguimos
TDMA?
el contrato porque tiene que hacer la parte de
What's the
optimización
meaning of
y últimos
TDMA?
detalles para poner el sitio,
Who
o sea,
knows?
el servicio de Claro.
Time
Cuando se pone
division
es
multiple
porque este
access.
sitio ya
Yes.
pasó uno
Yes.
por la validación
Use
otra
a
vez.
different time
RF,
to
lo que
distinguish
revisan los
the
cortes
user.
fotográficos
Right.
que
Yes.
se
Yes,
instalan
you
en las
already know.
antenas y se
TDMA.
hacen
For
las
the
antenas
GSM,
y
they
se
use the
aplican
TDMA.
etiquetas. Todo eso lo
And
hace.
this
Si
technology
tiene
to
alarma,
achieve the
también
digital
la
transmission
antena,
of the voice
si tiene
and the
ruido,
channels,
todo eso
right?
verifica.
2G for the voice and channels.
Observa ahí. Y no
So
puede
there are some
poner acá,
technical
poner.
features.
¿Cómo
Some
modificas ese
technical
dashboard?
features. First is the digital
no.
transmission.
Hasta acá,
Both the
esto sí
voice
modificamos.
and the signaling are
Es el
digitally
296 que representa
encoded.
los sitios que están
We have to
en esa fase.
encode,
Estos números.
code the
Ahorita
information.
que tenemos un
Both
falsificado
voice and
está
signaling are
sin
digitally
contingencia.
encoded.
Algo ha pasado
It
y
will
cuando
improve the
instalamos
call quality
online,
and
se pone
improve
acá
the
un
security. Right.
O sea, mira, en el
And the second one is about the frequency results. For the GSM, it supports the multiband. Support the multiband. Like the GSM 900 MHz, like the 1800 MHz, like 1.9
gigahertz.
So it supports multi-band, multiple frequency bands. So it catering to the different regional needs. Then for the network architecture, maybe the next several pages, we will show you the architecture evolution. Here we just mentioned for the GSM, it consists of the mobile station, the base station, and the mobile station MS, and the base station subsystem BSS, and the controller, the center, mobile switching center MSC. These three parts components in GSM. And the MSC is responsible for the whole setup for the routing allocation. Okay, this is for the GSM. Okay, the second one is the CDMA, IS95. CDMA. What's the of the CDMA?
Nosotros sí nos dieron, porque nosotros
CDMA is time division multiple access. So for the CDMA is code, right? Code division. Multiple, yes, multiple access.
Y ahí pues digo TTI.
And it is purposed by the Qualcomm, right? It's the world's first second generation mobile communication standard based on the CDMA. This is the first one, CDMA IS95. And the supported serial bandwidth is 1.25 megahertz. 1.25 megahertz. And for the CDMA IS95, TDMA IS136, these two, the middle two, they support the same uplink and downlink frequency bands. Also, they support both voice and the low-speed data services. One is voice, one is the low-speed data services. Okay, and for the CDMA, the multiple access technology is users. The UEs are distinguished by the orthogonal codes. Okay, by the orthogonal codes, and it will improve the spectrum utilization, and no need the frequency planning. This is advantages of the CDMA in 2G. You mean the 2G use FDMA too for the normalization, right? Yes. 2G also can use FDMA. But it is not very popular. The popularization is this four we list: the GSM, CDMA, TDMA, and PDC. Okay, it's more popular. The third one is the TDMA IS136, also the digital 2G mobile communication on the TDMA technology. And it is developed by the EIA, in the United States, in the US. And the serial bandwidth, we say for the second one, for the CDMA IS95, the serial bandwidth is only 1.25, right? Only 1.25. But for the third one, the IS136 with 30 kilohertz bandwidth, a little higher than the second one. So it is it can divide each physical channel into 6 time slots to support both voice and the low-speed data services, because the serial bandwidth is a little higher than the second one, right? So it can divide each different physical channel into 6 time slots. Then this time slot to support the voice service, to support low-speed data services. Okay, the last one is the PDC. PDC is the personal digital cellular. It is only used in Japan. Okay, the PDC only developed in Japan. Also, for the PDC, also using the TDMA technology. And for the PDC, there are some core features. First one is for the frequency band. For the frequency band, uplink and downlink use a different frequency band, but in total, 800 megahertz. In total is 800 megahertz. And compare the 2G and 3G. You evolved from 2G to 3G. 2G, we say the PDC and IS 136, right? And we see the 3G. 3G, we see the WCDMA and the CDMA 2000. These two are evolved from the 2G, from the PDC, and from the TDMA IS 136. For the WCDMA, WCDMA is evolved from the PDC, And for the CDMA 2000, it is evolved from the TDMA IS 136. Okay, now we check the 3G. 3G, first one, WCDMA. The full name of the WCDMA is Wideband Code Division Multiple Access. It is one of the mainstream standards for the 3G, and it's developed by the 3GPP. After that, the next pages, I will show you what's the meaning of the 3GPP, just the protocol. And by the 3GPP, we already defined some release and use this release to define the conceptions of the different rats. And for the WCDMA, I want to introduce the four core features for you. Why we use the WCDMA? Why WCDMA is so popular? First we focus on the transmission rate. WCDMA supports the high data transmission rate. The bandwidth is 5 megahertz bandwidth. Use the 5 megahertz bandwidth. And WCDMA achieves the theoretical downlink rate of up to 14 per second, 14.4 bit per second. But we see for the CDMA 2000, CDMA 2000 is only 3.1. Yeah, I write here. Sorry. That's one. Yeah, WCDMA 0.4 bit per second. But for the CDMA 2000, it's only 3.1 megabit per second. The rate have the huge difference. And for the TD-SCDMA, the TD-SCDMA is only 1.8 megabit per second. So this is the first reason why the WCDMA is so popular, because the WCDMA can support the high data transmission rates. And the second one is for the flexible channel allocation. WCDMA supports various channel types, support both the common channels and the dedicated channels to adapt to different service requirements. Maybe for the voice, for the conversational, and for the streaming media. So it can optimize the resource scheduling. This is the second advantages of the WCDMA, flexible channel allocation. And also, when we employ the fast power control at 1.5 megahertz, both uplink and downlink, effectively resisting the signal fading and interference. So also another one, focus on the power control, because we employ the fast power control at 1.5 megahertz, can resist the signal fading, resist the interference. So after that, under these cases, we can improve the coverage area, can improve the system capacity. This is the third aspect. The last one, the fourth one, is the global roaming capability. Global roaming capability. By the 3G, WCDMA has been deployed over 245 operators worldwide, with a coverage area far exceeding than the CDMA 2000, than the TD-SCDMA. So we need to remember these four aspects. One is the high data transmission rate. Second one is for the flexible channel allocation. Third one is the comprehensive power control. Fourth one is the global roaming capability. This is advantages for the WCDMA. Then for the CDMA 2000, also the same functions, support both voice and data services. And it can support the maximum data rate of up to 2 megabits. And for the CDMA 2000, also focus on the power control. Focus on the power control. It supports the fast closed loop power control. 800 megahertz are used on the forward link to enhance anti-interference capabilities. And we want to see the network architecture, the coverage optimization. We for the CDMA 2000, we employ the distributed base station architecture to support the faster handoffs to ensure the mobility. And for the market applications, we have the major regions during the 3G is United States, like the Canada, Japan, South Korea, China Telecom networks. So with a peak user base of more than 200 million. But now the current status is replaced by the 4G, replaced by the 5G network. Then for the last one, the TD-SCDMA. TD-SCDMA, we see phoneme, time division, synchronized code division, multiple access. So it used the TDD duplex mode. What's the meaning of the TDD? We will introduce later. We have the duplex mode. One is FDD, one is TDD. They have a little difference. Both TDD and FDD have their own advantages and the disadvantages. But now in 5G, TDD is more popular than the FDD. We will introduce the reason later. Here you need to know for the TD-SCDMA used the TDD duplex mode. First of all, the TD-SCDMA also it can support the high spectral efficiency, because we say the TD-SCDMA use the TDD duplex mode, and the TDD mode doesn't require the same frequency bands on the uplink and downlink, not required the same frequency band. But for the FDD, FDD, they must use the same, right? But TDD will just use a different time to distinguish the uplink and downlink. Okay. And also, the TD-SCDMA supports the flexible time slot allocation. This is related to the frequency results and the time domain results. Frequency domain results and time domain results. And we see that TDD, we use the time to make the difference, right? To make the difference of uplink transmission, downlink transmission. So we need to allocate the different time slot for transmission. Maybe within one subframe, there are 10 time slot, and maybe first 8 time slot for downlink transmission, and the remaining 2 for uplink. Maybe we can change allocate the first 7 slot for downlink and the remaining 3 for uplink, right? So it supports the flexible time slot allocation. It can improve the spectrum utilization by 20% compared to the FDD. This is the advantages of the TDD. So for the TD-SADMA, it can support the high spectral efficiency. Also for the TDD, we have a new key technologies. We say the beamforming. Beamforming for the TD-SADMA, it used the smart antennas because beamforming can reduce the interference and enhance the signal quality. So here, TD-SADMA use the smart antennas. And also we can design the narrow bandwidth. 1.6 MHz bandwidth is suitable for dense urban areas with weak breathing effects. Okay, then for the 4G and the 5G, it's very familiar, right? Familiar with you. For the 4G LTE, right? The LTE. What's the full name of LTE? Long-term evolution, right? And 5G. 5G, we also say the NR, right? The new radio is 5G. And 4G, we use the two main streams. One is FDD, one is TDD. So here say the TD-LTE. TD-LTE. And later we will introduce the definition of FDD and TDD. Okay. And 5G, we just say that the NR. Say that the NR. Okay. And beside the different rates of the 1G, 2G, 3G, 4G, 5G, we also right here, the yellow part, right? The technology driven, requirement driven, right? What's the meaning of technology driven? What's the meaning of the requirement driven? First, we see from the 2G to from the 1G to 2G. It's technology driven. We say 2G, we reused the frequency, right? We reduce the frequency. Then we can improve the spectrum efficiency. This is the technology driven, right? And from 2G to 3G, it's the requirement driven. What's the requirement driven? First is about the service, right? The service requirement. We say 2G. 2G, the typical service is SMS, right? SMS, the short message. And for the 3G, 3G people requires the video call, right? The video call and the surf the internet and the send the email, right? So from 2G to 3G, we need to upgrade the service requirement. Upgrade the service requirement. And for the technical, one is the spectral efficiency. Spectral efficiency. The later pages we will show you. In 1G, 2G, 3G, 4G, 5G, we use the different domain. One is CS domain and PS domain. And for the voice, we use the IMS. And in 2G used the CS domain, right? Based on the CS domain. The 2G core network based on the CS. But 3G we introduced the PS. PS is a packet switching, right? The PS is a little difference. And from 3G to 4G, also the requirement driven. First, we need to focus on the speed and capacity, right? The speed and capacity. The theoretical peak rate of 3G network is only 2 megabits, per second, which is insufficient to support the high definition video, right? Cannot meet the requirement of HD video. Besides the HD video, also online gaming and other services, right? We cannot meet the requirement. So 4G achieved the speed exceeding 100 megabits through some new key technologies, maybe like the OFDMA, like the MIMO technologies, can meeting the requirement of the high growth demand of the mobile internet. The channel is no longer separated during an entire call in PS, right? Sorry. Hi, Daniel. Sorry, I don't get to what's a minute. What's your question, minute? You mean what's the meaning of the separate, no longer separate during the entire call in PS? Can Raimo to explain your question? From CS to PS, I think that's also reason. Are driven by the efficiency. What would be the future of the technology? You mean the new key technology? Driven by efficiency. For the efficiency, also we already focus on the efficiency. Right? Efficiency is for the technical driven, right? For the technical, we proposed the new key technology to improve the efficiency, the transmission efficiency. We will introduce later. Here I say the speed, right? The speed is the transmission efficiency. We have the MIMO key technologies, and in 5G we introduce the massive MIMO. Massive MIMO in 5G we can reach the at most 16 layers and transmit at the same time, but 4G at most 4 layers. So now for 5G, the transmission rate already 4 times than 4G. If we use the same base station, use the same terminal. Yes, the technology driver already focused on the efficiency. Also, we say that the OFDMA, right? OFDMA. And for the device, we have the different size, different types of the device, and also focus on the cable. Maybe later we will introduce the changes of the antenna and the changes of the base station, both outdoor and indoor. Like 5G, we use the AAU to instead the 4G RU at antenna, right? Because there are a little the feeder needed the feeder to connect to the RU and the antenna, so it will cause the feeder loss, right? So we need to compensate the feeder loss during the transmission. But in 5G, we use the AAU to instead integrate the RU and the antenna together, can improve the transmission efficiency as well. So many aspects to improve the efficiency. Switching from the CS to PS, I think that was the reason for efficiency. Yeah, also. Yes. From we already switched from the CS to the PS, right? To the 4G and 5G canceled the CS. Cancel CS already focus on the PS to do the transmission. Okay, this is the first one from 3G to 4G. Focus on the breakthrough in speed and capacity. And the second one is the technology architecture innovation. We say 3G. 3G used the CS and PS switching, right? But 4G is full IP-based architecture. Full IP-based architecture. The 4G core network is EPC, right? It's the EPC. It can reduce the latency, right? Reduce the latency. In 3G, the latency, in 3G, the latency may be 100 milliseconds, but in 4G, we can reduce the latency until 30 milliseconds to 50 milliseconds. So it can reduce the latency. Now also can improve the resource scheduling efficiency. This is based on the IP-based core network. Another one is the spectral efficiency. Spectral efficiency because we used the OFDMA or signal frequency division multiple access. Use the OFDMA technology to enable more flexible frequency band allocation. So from these two aspects. And also we have the extent of the service scenarios, right? 3G are focused on the voice and the basic data services, but 4G supports the multimedia application, like the HD video stream, like the cloud computing, mobile payments, right? It will drive the popularization of the Internet of Things and the smart device. Also we can focus on the operator computation, also the cost optimization. We see 4G base station use the flat architecture, components, two components, BBU and the RU. Right? It can reduce the intermediate equipment and lowering deployment and reduce the maintenance cost. Right. Also in 4G, we have the CUPS, control plane and the user plane separate, CUPS. Okay, this is the requirement driven from 3G to 4G transmission. And the last one, the driven from 4G to 5G, technology driven from 4G to 5G. The first one also the speed and the capacity requirements, right? The peak rate of 4G network is around 1 gigabit, but 5G we already introduced the ultra high frequency resource, the millimeter wave. And also we introduced a new key technology, the massive MIMO. So we can increase the peak rate to over 10 gigabits. So almost 10 times of 4G. 4G network is 1 gigabit, but 5G is 10 gigabits. So it can meet the demands of the UHD service, right? The ultra high definition is like 8K video, like the 8K video. First is the speed and capacity requirements. The second one is about the latency and the high reliability. When we say the low latency and high reliability, what can you see? Which belongs to which typical scenarios? Oh, I'm not switch my screen. Here I'm introduced the technology driven from 4G to 5G. This part. IoT, you mean the IoT? I see the ultra high reliability and the low latency. Actually is URLC. We see the 3GPP already defined the three typical scenarios for 5G, right? The eMBB, MMTC, and the URLC. Use the R15 to R17 to define these three typical scenarios. And for the URLC, the full name is ultra high reliable and low latency. So here for the 5G, we focus on the low latency and high reliability. Wider bandwidth for lower latency. Wider bandwidth actually is for the eMBB, enhanced mobile broadband. And for the eMBB, like for the AR, for the VR, for the smart city, like that. And for the URLC, the scenarios like the autonomous driving, the self-driving, and for the remote industrial. And for the MMTC is massive machine. Okay. Here, the second aspect I want to say is for the low latency and high reliability. 5G can reduce the air interface latency from 10 milliseconds to 1 millisecond. So 5G can support the scenarios with a high real-time requirements, like the industrial internet, autonomous driving, like this. And also, the driving from the technical drivers for the evolution from 4G to 5G is network architecture innovation in the network architecture. First, focus on the core network. Focus on the core network. 5G, we have the cloud-based core network. Cloud-based core network. 5G introduced the SBA, the new conception SBA. SBA we will introduce later. Sorry. Sorry. I will type in the chat box. Okay. For this one. Okay. See, I'm texting the chat box. The SBA. This one. 5G adopts the SBA, and the SBA full name is a service-based architecture. Service-based architecture. That means for all the network functions in 5G core network, they used the same standards of the ports of the interface NG. The next full name is next generation, and we use the NG to name the interface. But we say in 4G, the interface between each two core network elements, they have the dedicated name, right? They have the dedicated interface. But in 5G, we use the NG to indicate. Use the NG to indicate. So we introduced the SBA, and also we introduced a new key technologies. We say the network slicing, right? The network slicing technologies. It can enable the on-demand resource allocation. But 4G relies on the traditional EPC architecture. So in the network architecture, we have the innovation. Cloud-based core network. And besides the SBA, besides the network slicing, we also introduced the CUPS, right? CUPS we said before, separate the control plane and the user plane. And in 5G, we can allocate the UPF. UPF is only one enough of the user plane. UPF. In 5G, we can deploy the UPF nearest to the UE, nearest to the enterprise, to reduce the transmission delay. Also for the spectrum efficiency, the technology driven from 4G to 5G, we introduced a new frequency results. In 4G, we already used the low frequency band, right? From 1G to 4G, the frequency band we use all belongs to low frequency bands, FR1, right? 3GPP has defined the frequency to FR1 and FR2. FR1 indicates the frequency results lower than 6 GHz, and FR2 is above 6 GHz, right? And especially for the millimeter wave, FR2. And 5G achieves the coordination between the FR1 and FR2 through the DSS. Do you know what is DSS? What's the meaning of the DSS? Dynamic spectrum sharing, the new key technology. Dynamic spectrum sharing. And also we support the carrier aggregation like the 3CC. These key technologies can improve the spectrum utilization by 3 to 5 times compared to 4G. So 5G can improve the spectrum efficiency than 4G. Also, empowerment of the vertical industries, right? This is the topic we want to introduce on tomorrow morning, right? The 5G industry development. So here, 5G can support the massive IoT, right? Some students said before, the IoT. 5G supports the massive IoT connections. And we say that the ideal reaches millions of devices per square kilometer, can promote the implementation of applications like the smart cities, like the remote healthcare. But 4G is mainly focused on the consumer level mobile internet, right? 4G focus on the consumer level. 5G can support the massive IoT connections. But evolved from 4G to 5G. If we want to achieve these advantages, achieve this target, we need to use some key technology to solve some problems. First one is frequency band. We said 5G support the FR2, support the millimeter wave deployment. But when we deploy the millimeter wave, there are some disadvantages. First one is the short coverage area. We say in before 5G, 3G, 4G, we all use the low frequency band, and the lower the frequency band, the larger the coverage area, the larger the cell radius. But in 5G, when we want to use the millimeter wave to deploy the radio network, we need to solve the problem. We said uplink and downlink decoupling. We need to solve this problem. How can we solve this problem? We will introduce later. And the second problem we need to solve is the latency, right? How can we short the latency? How can we reduce the transmission delay? We support the network slicing. We can allocate the dedicated network slice for the different typical scenarios, like eMBB, like the UIOC, like the MMTC, like the V2X. In China, we already have 4 types of the network slice. One for eMBB, one for UIOC, one for MMTC, and one for V2X. Do you know what is V2X? Do you know what's the meaning of the V2X? eMBB, MMTC. URLC. No? All right. Actually, the V means vehicle. V means vehicle. V2X means vehicle to everything. Vehicle to vehicle, vehicle to person, vehicle to internet. So we say the V2X. V2X is for the self-driving, for autonomous driving. So we already have these 4 types of the network slice. And also we have another one is about the AI, about the AI integration, because 5G optimized the resource scheduling and the interference management through the AI, right? Through the AI. But 4G only relies on the traditional algorithm. So here we just put several times to introduce the technical driven, the technology driven, and the requirement driven. For the requirement driven, just we have some new service applications, some new service scenarios. So we need to evolve from 2G to 3G, from 3G to 4G, 4G to 5G. But the technical driven is focused on the efficiency, focused on the speed, focused on the capability, right? Focus on the spectrum efficiency, focus on the network architecture, and some new service scenarios, especially the vertical industry, right? Especially the vertical industry. Okay, this is for the evolution of mobile communication. Okay, here show you the different generations. We have the different services, right? Different services. 2G service is SMS and voice, right? Focus on the voice call and the short message. Can only support the low-speed data transmission. And for the 3G service First, to integrate the voice and the data, so it can support the video call, support the mobile internet. The peak rate reach up to 2 megabits per second. Also support the multimedia service like the streaming media, the mobile email. And for 4G, service, we say 4G are all IP-based network, so can support the high-speed data transmission. The peak rate reach up to 1 gigabits. So it can support the HD video, the cloud service, the mobile payments. For the short videos, mobile live streaming, the online gaming, and smart home control, smartphone control. And for the 5G service, we say the eMBB, UILC, MMTC, right? These three typical applications. For the eMBB, is for the AR, for the VR, for the smart city, for the smart home, for the HD video. And for the UILC, like the remote industrial control, like the autonomous driving and the self-driving, we need to control the latency lower than 1 millisecond, right? Lower than 1 millisecond. And for the MMTC, also like the smart water meter, smart meter, and the large-scale IoT, And besides these three typical scenarios, we also have the industry applications, right? The 5G smart factory, the 5G digital farms, the underground mine communications. This is a 5G service. So we can find from 2G to 5G, service have expanded from the signal purpose communication to the intelligent applications, right? 5G can achieve the IOV, the Internet of Everything, through these three core scenarios: eMBB, UILC, MMTC. This is the service change. Okay. And here we see the CS and PS before, right? For CS and PS. And here, first we check the 2G and 3G. 2G and 3G are coexistence of CS and PS domain, right? First, we see the voice service. The voice service carried in the CS domain use the dedicated resource allocation. So it can ensure the real-time performance, but have the low resource utilization, right? This is for the voice service. Then for the data service, it carried in the PS domain, packet switched domain. It used the multiplexing technology, so it can support the efficient data transmission. But for the voice service and data service, we have the handover priority. Switch from CS to PS. The voice service in the CS domain have a little higher priority than the data service in the PS domain. For example, when a VoIP call is ongoing, it will interrupt it if the voice call is initiated, right? Voice call is in the CS domain, but the VoIP is in the PS domain. So when the VoIP call is ongoing, it may be interrupted if the voice call is initiated. Okay, this is the handover priority of the CS and PS. Okay, then we'll check the 4G. We check the 4G. 4G, we not have the CS domain, right? Only the PS. 4G, the voice call, we used the VoLTE, right? You already know the VoLTE, right? The VoLTE technology. The voice service are implemented through the IMS. Do you know the IMS? Yes. Okay. So in 4G, the voice service are implemented through the IMS in the PS domain. So it relies entirely on the packet switching on the PS, and no need to fall back to the CS domain of the 2G or 3G. But besides the VoLTE, we also support one scheme we say the CS fallback. Do you know the CS fallback? CSFB. Do you know the CS fallback? Especially in 4G. No? Okay. We say VoLTE. VoLTE means voice only implement in the IMS in the PS domain, so it will not switch to the 2G, to the 3G, to the CS domain, right? But in some cases, maybe the UE, the device, not to support the VoLTE. Not to support the VoLTE. The feature is not supported. In this case, the UE will initiate the voice call in 4G in the PS domain, but the call network, the MME, will give a reject response to the UE. UE received the reject response. In this case, UE will send the call network will ask the UE, inform the UE fallback to 2G, fallback to 3G network to perform the voice call, to initiate the voice call. This technology we say the CS fallback. CS fallback. So some 4G terminals need to fall back to the CS domain of 2G or 3G to receive the voice call, during which data service are suspended. So during the CS fallback, the data service are suspended and fall back to 2G, 3G, fall back to the CS domain to receive the voice call. This we say the CS fallback. Especially in 5G. In 5G, we have another similar schemes. We say the EPS fallback. 4G, we say the CS fallback, right? 5G, we have the EPS fallback. This one. Because 4G, we have the VoLTE, right? And 5G, we have a new voice schemes. We say the VONR. You can check the 5G VONR, right? VO. But in some cases, the terminal not support the VONR, or maybe for the 5G network, they not support the VONR features. In this case, UE will initiate the process, the voice call to the IMS in the only 5G radio network to perform the registration to the 5G IMS. But the 5GC, the 5G call network, send the reject information to UE and inform the UE fallback to 4G, perform the VoLTE service. This scheme we say the EPS fallback, very similar from 4G to 2G or 4G to 3G. Okay, one is CS fallback, one is the EPS fallback. Okay. And 5G, we say the CS domain is completely cancelled, right? And both voice and data service are carried in the PS domain. And we have the NFV. NFV means network function virtualization. NFV, based on the NFV. And also we introduced a new unit. We stated the QoS, only for the session management. For the PDU session, we have the QoS. Okay, this is for the service domain evolution. Here, show you the structure, right? Show you the structure. From the terminal to the service is end-to-end structure. Terminal to base station. From terminal to base station is the radio network, right? Radio network. And from the base station to the transport, this is a transmission network. From transport to the call network, then to the high layer for the application for the service, And here we want to we need to focus on 3 rules. One is call network. Call network is the central brain, right? It's like our brain. It's the center, the call network. And and for the transmission, it's like the high network, wireless network. This is like a network of the wireless signal tower converting a city. It converts the radio wave from your phone into the digital signals through the base station. So it is responsible for receiving your voice and your video request and adjust the signal strength, then switch between the seamlessly switching between the base station as you move, right? So just 3 process. One is for the access, then perform the resource management and perform the mobility management. This is some process during the wireless network. So it's just like a courier rides an electrical bike through the streets, and the wireless network frees information from the limits of the cables, right? Fixed network just use the fiber, right? Use the fiber to transmission. But here, the wireless network can free the information from the limits of the cable of the fiber. Yeah. Then for the transmission, we see transmission is similar to the highway. It's like the super highway connection cities. Composed of the equipment like the optical fibers and the routers. It carries the data stream, carries the massive data stream, and can use the multiple lanes for the transmission and the intelligent navigation to ensure the information travels at the high speed from the base station to the core network. There's a function of the transmission network, just like the trucks, right? Just like the trucks on the highway to avoid the traffic jams. The transmission network automatically selected the optimal path, choose the best transmission path. The last one is the central brain, the core network. It's like the central sorting center of the courier company. So the core network is responsible for receiving, for identifying, and distributing the data packets. It verifies the identities of the sender, the identities of the receiver. And this process we say the authentication, right? Authentication. After UE send the registration to the core network, the network need to perform the authentication, right? Then we'll allocate the ID for the UE. Then UE can search the internet, right? And besides the authentication, the core network needs to plan the optimal route. It's routing, and also need to recode the weight of the packet, like the bill, right? Like the bill. So the core network can ensure the information is accurately delivered to the destination. For example, when you make a phone call, the core network will establish the dedicated channel and continuously monitor the connection status. In 5G, we already defined the status like the RRC layer. For the RRC layer, connected mode, disconnected mode, and the inactive mode. The core network needs to continuously monitor the connection status. Okay, this is for the infrastructure from terminal to base station to transport to core network, right? Wireless network, transmission network, and core network. And here I show you the just use the geographical region to show you the radio network architecture. Here we can see the left part from the province to city to district to the country, right? Divided into 3 levels. From top to bottom is the province at the top. Province at the top. The province at the top, it governs multiple regions, the city 1, city 2. And each region will cover several districts and countries, then can forming the management system. And the network functional architecture corresponds to a 3-layer core structure. The core network layer, aggregation layer, access layer. First of all, the core network layer, it is centered around the core network, achieves the backbone data exchange through the core ring, So it connects upwards to the service cloud, and serve as the central system of the network. And for the aggregation layer, located below the core network and upper the access layer. The aggregation layer aggregates the data traffic within the region through the aggregation ring, playing a transmission role between the upper and the lower layers. And we say that the equipment is deployed in the aggregation equipment room. And that's for the access layer. It's as the endpoint of the network, right? Access layer. And it connects the base station equipment distributed at the edge site through the access ring, directly interfacing with user terminals to provide the wireless signal access, provide the coverage. Right? So the overall architecture ensures the efficient management of the communication network to ensure the stable data transmission and extensive service coverage. Okay. It's very easy, right? It's very easy. And here just to show you the version evolution, right? The first line is 2G, 3G, 4G, 5G. Then the phase, right? R means release, right? What we say before 3GPP defined release, define the release, and this release will define the first phase of the 2G, second phase of 2G, third phase of 2G, right? And the same for 3G, for 4G, for 5G. And also for the different RATs, for 2G GSM, GPRS, AMR, we introduced before, and the related rate, and the cell bandwidth, On this page, we need to remember the maximum cell bandwidth of 4G and 5G. Okay, we need to remember 4G. The maximum cell bandwidth is 20 megahertz. In 5G, we see two values. One is 100 megahertz. Second one is 400 megahertz. We see 4G, we can deploy the network by using the FR1 and FR2, right? When we use the FR1, the maximum cell bandwidth is 100 megahertz. But when we use the FR2 to deploy the network, the maximum cell bandwidth is 400 megahertz. Okay. Low frequency band, 100 megahertz. 400 megahertz is for the millimeter wave. Okay, for the millimeter wave. And besides the maximum cell bandwidth, in 4G, it canceled the cell bandwidth below 5 megahertz. So at least 5 megahertz. Okay, at least 5 megahertz in 5G. At most 100 megahertz or 400 megahertz. Okay. And for the cell bandwidth utilization, do you know the utilization in 4G and 5G? For 4G, we allocate 20 megahertz per cell, but the actual use bandwidth is only 18 megahertz, right? So the efficiency is 90%, right? 90%. Actual 2 bandwidth is for the guard band, for the band. And in 5G especially, we talk about the FR1. The maximum cell bandwidth is 100 megahertz, right? 100 megahertz. But the efficiency is only this value. This value. So we say in 4G, we introduce some key technology to improve the spectrum efficiency. Like the FOFDM, and we introduce the new results, new frequency results, new time domain results, and we introduce the new frame structure, and we introduce the the new key technology like the massive MIMO. All these key technologies combined together to achieve the efficiency, the high efficiency than 4G. Okay. And for the CS domain, PS domain, we already introduced it before, right? We already introduced before. And the network structure, for the network structure, for the 2G MS is mobile station. It's similar to the 4G, 5G UE, the user. And for the BTS is the base station, and the BSC is the base station controller. And for the 3G, we change the name, base station to the node B, And 4G we evolved from 3G, right? So we say the E node B, and 5G is the next generation, right? NG, next generation. So 5G we say the G node B, And for the RNC also for the similar to the BSC in 2G. And here we can check the IMS, right? Check the IMS because we now switch from the CS to the PS. Right? And here we focus on the NE in 4G and NF in 5G. Here below the 4G, we can find the yellow word, the MME, SGW, and the PGW. Do you know what's the meaning of these three elements? What's the function for MME? Do you know the MME? It's for the mobility management. Yes, one is for the second M is management. The first one is for the mobility management entity. Yes, yes. Someone already write the full name, right? Write the correct full name. Yes. Okay, and for the MME, it belongs to the core network, right? Belongs to the control plan. Then for the PGW, SGW contains both control plan and user plan, right? So we say the PGWC, SGWC. This is for the control plan. PGWU, SGWU is for the user plan. Now we check 5G. Here, not to write specified the network function for the 5G core network. Here, just say the CP and the UP. 5GC CP means the control plan network function in 5GC. UP means the user plan function in the 5GC. Here, only one network functions belongs to the 5GC UP. Is the UPF. Only one network function belongs to the user plan. UPF. The others, like the AMF, AMF, SMF, PCF, all belongs to the control plan. So that we see the CUPS. And the CUPS, after we we deploy the CUPS, we can deploy the UPF near to the user, near to the enterprise to shut the transmission delay. Okay, this is for the version evolution from the phase 1, 2 to R15. Here, just to write the R15, but we know we already proposed to R18, right? Now is to R18. But for 5G, we have three phases: R15, R16, R17. For R15, the core target is the basic structure for the EMBB, is for the R15, and the typical technologies like the massive MIMO, like the millimeter wave, in the R15, and in the R16 to define the URLC enhanced for the V2X, And for the R17, R17 is for the MMTC, and the typical technology like the radar cap, like the NTN, like this. And now we already proposed the R18, right? Do you know the R18? And for the R18 is talk about the 5G advanced, 5G advanced, like the AI, like the AI. Yes, 5.5. Yes, 5.5 gigahertz. 5.5G is also called 5G advanced. 5G advanced. Okay. Yeah, this page just need to know the 3GPP. You just need to know what is 3GPP, the third generation partnership project. And through the 3GPP, we can realize the smooth 2G to 3G transmission and the indirect roaming like that. And have 3 TSG, one for radio access for the RAN side, and for service and system aspect, and for the core and the terminal, the TSG. And each TSG, we have the several different work group. You just need to know what is the 3GPP, and 3GPP can define the release. And different release used to definite to initiate the different generation, 1G, 2G, 3G, 4G, 5G. Now it's to release 18. Okay, to release 18. Okay, now is we already ongoing 1 hour, 1.5 hours. So maybe we have a short break for 10 minutes. For 10 minutes, then we continue the remaining parts. Okay. Okay. All right. Hello guys, are you back? Please give me some response in the chat box. Yes. Okay, most of you are back. Okay, now we continue. Okay, continue the second part. Okay. Okay, on this page, we just to talk about the service-oriented network architecture, especially for the SBA. We said before, right? The service-based architecture. And we see 5G, we take a new 5G core network architecture. And the 5G network architecture adopts the SBA, with the SBA serving as the foundational framework for the 5G networks. And essence of the SBA lies in defining the network functions as flexible, reusable, and independently manageable service models based on three principles: self-containment, reusability, and independent management. Okay, these three principles. This will allow the operator to flexibly customize the network configurations according to the business needs. And in the SBA, the interaction between the network functions are implemented through the service core. And each network functions presents the common service-oriented interface that can be evoked by authorized network functions or services. Right? But in construct, on the update, traditional 2G, 3G, 4G network architectures use the point-to-point architecture, right? Use the point-to-point architecture. Then the interface between the network elements must be predefined and configured. Use a different interface. These interfaces are typically designed for use only between the specific pairs of the network elements, offering the limited flexibility. So here, 5G, we use SBA. And here said all access modes supported. And the all service supported. How can we support it? The all access mode supported the all services. We need 4 key technologies just here, right? Cloud native, CUPS, MEC, and slicing. So next time, so now we will introduce these 4 key technologies. Okay. First one, cloud native. Here just compared the 4G core network and 5G core network. 4G core network, here you can find the interface between base station to the SGW is S1U. And base station to MME is S1 MME. So 4G core network adopts the flattened architecture, separate control from barrier. And the MME is responsible for the signaling control, but the SGW PGW handles data forwarding. However, these network elements are connected through the dedicated interface, maybe S1, maybe X2. So use a different interface to connect to each other. But a 5G core network, now we see the right part, the 5G core network use the SBA architecture. The network functions decoupled and integrated through the modularization. Decoupled network functions can be independently expanded, independently evolved, and deployed on demand. So all the network functions on the control plane interact with each other through the service interface. And the service can be evoked by multiple network functions to reduce the coupling degree defined for inter-NF interfaces. So this is the difference between the 5G core network and the 4G core network, 5GC and EPC. 5GC is more flexible, very easy to deploy and enable the faster deployment. Okay, this is the cloud native. Then we check the CUPS. CUPS full name is Control Plane and User Plane Separation. CUPS is a key technologies in the 5GC. The core concept is to split network functions into the control plane and user plane to achieve the flexible resource management and the service optimization. And the control plane is responsible for the signaling processing, like the session management, like the mobility control, and consists of the lightweight network elements, such as the AMF, such as the SMF. Okay. AMF is similar to the function of MME, right, for the access management, and SMF for the session management, like the PGW SWC, the control plane of PGW SW. We use the SMF in 5G, which are centrally deployed to ensure the global policy consistency. And the user plane is responsible for the data forwarding. Is the UPF, such as the traffic offloading, the QoS assurance, and is implemented by the UPF network element. Can be deployed at the edge to reduce the latency, such as the MEC. And why we used the CUPS? We have two main reasons for adopting CUPS. One is the service requirements. We say 5G needs to support the scenarios such as the eMBB, require the high bandwidth, the UILC, ultra low latency, MMTC, massive connectivity, right, which cannot be dynamically adapted to by the traditional 4G architecture. This is first reason, right? The service requirement. And second one is improve the resource utilization. After separation, the control plane can optimize the signaling efficiency in a centralized manner. Here you can find the CP. Yeah, the CP here. The AMF, SMF, UDM all belongs to the control plane network functions, right? So after separation, the control plane can optimize signaling efficiency in the centralized manner. But the user plane can be expanded in a distributed manner on demand, like the like the UPF. We can deploy it at the edge DC, near to the base station, near to the user, to the enterprise. So compared to the 4G architecture, the 4G EPC control plane and user plane are tightly coupled, limited the coupling, and the results in the higher latency, right? Higher latency. In 4G, the latency around 30 to 50 milliseconds. 30 to 50 milliseconds. But after adopting the CUPS in 5G, we completely separate the control plane, user plane. UPF deploy at edge nodes close to the user, reduced the latency by more than 90%. Also, besides this part, also we have the dynamic slice adjustment. So this transmission from the general purpose to the on-demand service enable the 5G network to provide the customized capabilities for vertical industries. for vertical industries. So here for the control plane like the AMF, SMF, UDM, we deploy as a central DC, perform the centralized process. And for the UP, like the charging, like the ankle on the local DC, and the UPF deployed at the HDC, native MEC capability. Okay. Next one for the MEC. MEC in 5G, the enterprise faced not only the increase in connection speeds, but also the extreme demand for the real-time performance, the security, and the flexibility. Right? The MEC address these needs by bringing computing capabilities to the network edge, creating an intelligent, efficient, the open platform for the digital transformation for the enterprises. So first, we need to consider how does the MEC accurately meet the needs of the enterprise, right? The enterprise requirements. For the industries such as the industrial manufacturing, the healthcare, the energy, which are highly sensitive to the latency, right? Highly sensitive to the latency. In this case, the MEC brings the UPF down to the edge of factories or the campus, enable localized data processing. This will reduce the latency from 10 milliseconds in traditional cloud environments to less than 5 milliseconds. For example, in the smart factories, the MEC ensures real-time response for scenarios, such as the control of the robotic arms and the AR-based remote inspections, preventing the downtime caused by the network fluctuation. In addition, sensitive data can be processed at the edge. So it will not only eliminate security risk associated with the core network transmission, can also save over around 40% of the backhaul bandwidth costs. Furthermore, the MEC can support the network slice technologies, right? We said before, support the network slice. So it can provide the enterprise with dedicated networks, right? The customized network. So the enterprise can customize the dedicated slice results based on their business priorities. For instance, for high priority bandwidth can be allocated to the URLC slice to ensure zero packet loss for the industrial control signals. And maybe the slice like the large capacity channels can be reserved for the eMBB service, for the eMBB slice to support the real-time 4K video transmission. This on-demand allocation capability transformed the enterprise network from the one-size-fits-all approach to the customized one, right? To a customized one. Okay. This is for the enterprise. Then for the operator, operator is entering the to-be field, right? Can sell the customized slice to the enterprise, entering the to-be field and the large-scale enterprise applications. Also can control the radio network, retaining the control over the network. This is a MEC. MEC. Okay. Then for the slice, we see so many times of the slice. What is the slicing? What is network slice? Here we give you two pictures. As we all know, during the rush hours, all the vehicles are crammed onto the same road, like the left diagram. People, motorcycle, cars are mixed together, and first the traffic jam, right? Traffic jam, because the passage is overwhelmed by a signal flow of traffic, and no one can move quickly. But the right diagram, we see if we separate the road into dedicated lanes, the people, motorcycle, cars, each using their own dedicated lanes, the situation becomes completely different, right? All of them can travel as needed, and efficiency directly doubled. So 5G network slicing is like a traffic division for wireless network. Divides the main channel of the 5G network into the independent virtual networks. Different slices serve different scenarios and applications, right? For example, the autonomous driving requires ultra low latency, right? So the slice needs to provide with the priority channel, right? And maybe for the industrial automation requires the ultra high reliability. So the slice customize a dedicated line for it, right? And maybe for the regular mobile internet access. Regular mobile internet access requires the wide coverage. So the slice also provides with the public channel, right? Public channel. So in summary, the slicing allows the 5G network to function like the intelligent road, splits the congested main channel into the dedicated small channels, enable the different service travel on their own lines, not only avoid the mutual interface, also precisely meets the needs of the each services, maximize both network efficiency, also improve the user experience. So that's why we introduced the network slice. Okay, now we check the different type of the slice for the different service. First, we see the HD video. To meet the requirements of the HD video, it's for high bandwidth, for low latency, and high stability, right? So the network slice can customize dedicated bandwidth results, right? The dedicated bandwidth results, and forwarding the path to ensure smooth data transmission. The second, for the larger scale low-speed connection. For this one, it's similar to the smart meters, right? Such as the smart meters. Network slice can allocate lightweight resource to reduce the costs, and can improve the connection density. And the third one, for the real-time service, like the autonomous driving. To meet this service requirements, is for the ultra short latency and ultra high reliability, right? In this case, the network slicing need to provide the dedicated network channels with a low latency and high reliability. The control plan enhance the mobility management, while the user plan ensure the data forwarding latency. Work together, control plan and user plan. And edge data centers are deployed close to the vehicles, right? Edge data center deploy close to the vehicles because it can reduce the transmission delay, reduce the feedback delay. And the core data center provided the global computing power support to ensure the real-time performance and the safety of the self-driving decisions, right? So the control is on the center, in the center. For the transport, just now we talk about all belongs to the core network. Okay, for the core network. Now we see the transport network. 3 key points, 3 keywords: wider, more efficient, and more intelligent. First, for the wider. Wider, what's the meaning of the wider? Wider means ultra large bandwidth support, right? Ultra large bandwidth support. Yes, yes. And the bandwidth leap. The air interface rate of 5G is dozens of times higher than that of 4G. Right? The barrier network needs to be upgraded to support hundreds of gigabits bandwidth to achieve the signal wavelength transmission of around 200 gigabits, 400 gigabits, right? And for the more efficient is for the low latency and high reliability. The latency optimization. For the latency optimization, we need to deploy the UPF closer to the edge nodes, right? To the edge nodes. End-to-end latency can be reduced to below 1 millisecond in 5G. 4G is 10 milliseconds. After we deploy the UPF close to the edge nodes, we can reduce the delay below 1 millisecond. So it supports the URLC scenarios. And for the ultra high reliability, actually we can achieve 6.9 reliability. This value 99.9999 a second. This one, we achieve this reliability to ensure the crucial service such as the industrial control, such as the vehicle networking. This is for the more efficient. Last word, more intelligent means more smarter, right? Smarter. We use the network slice and the edge computing, right? The edge computing. For the slice isolation, the logical independent virtual networks are created using the NFV, the network function virtualization technologies, the NFV technologies to provide the customized bandwidth. Also need to guarantee the QoS for the different service to meet the different requirements, maybe for the healthcare or for the security. And also we see the edge computing belongs to the more intelligent. The edge computing is the MEC we said before, right? The multi-access edge computing. The MEC is deeply integrated with the barrier network. Bring the computing capability closer to the base station site to reduce the data transmission costs and can improve the local process efficiency. So just the 3 keywords: more wider, can allocate more cell bandwidth, more efficient. More efficient is to use the network slice to guarantee the low latency for the customized requirements and the ultra high reliability. And more intelligent is the smarter, the network slicing and the edge computing. Okay, then for the base station, we said beside the key technologies, beside the results, we also changed the device type. For the base station, outdoor and indoor, both outdoor and indoor. First, we check the outdoor base station. With the same function moved to the integrated antenna system. We check for the 2G, 3G, we use the BTS, but from other types like BBU, RU antenna. This mostly used in the 4G, right? In the LTE system, I use the BBU, RU antenna. And in the 5G, we integrated the RU and antenna together to generate the AAU. So there is no feeder to connect the antenna and RU. to realize the zero feeder loss. Zero feeder loss. Also, we see the RU size a little larger than the RU than the antenna, so the AU can contains how to say that contains more elements than the 4G, especially to 64 TRX. 64 TRX. And here we can find some words like the weighting, right? Do you know the weighting? Weighting is for the beam forming, right? For the beam forming. What's the function of the beam forming? Is to increase the coverage length of the beam. We say the original solution, we use the wide beam for the broadcasting, right? It's like a balloon. The power is fixed value. When the wide is 4 and compare with the wide is 2. When the wide is 2, the length of the balloon is larger than the wide is 4, right? With the same power. So when we perform the beam forming, we can increase the shear radius of the beam coverage area. So we use to perform the weighting for the beam. And for the 5G, the AAU, we have the transmit, receive, and the weighting. Besides the weighting, besides the beam gain, we also can receive the transmitter gain and the receiver gain. Because we have the multiplexing for both a single UE and multiple UE. Especially in 5G, we support the massive MIMO, so we can perform the MU MIMO. That means at the same time, multiple users, after paired, they can use the same time frequency results to transmit at the same time. So it can improve the system capacity, improve the transmission efficiency. This is for the base station outdoor form evolution. Now we'll check the indoor. Indoor, here we just need to focus on from the DAS evolved to the DIS. Compared with the traditional distribution system, the DIS can support the higher frequency band. For the DS, only support low frequency band. And when we upgrade the system, distribution system, we need to change the device. But for the DIS, it can allow the evolved to 5.5 GHz to 6 GHz. No need to change the device. Also, it can support a little high frequency band like the 3.5 GHz and the millimeter wave. This is the first one. And the second one is for the for the MIMO capability. For the MIMO ability, for the DAS, for the traditional distribution system, only support 1T1R. Do you know the 1T1R means one transmit, one receive, right? Just one channel. But for the DIS, for the digital indoor distribution system, we can support the 4T4R. That means at least 4 times than the DAS, right? Can improve the system capacity, improve the system throughput. Also for the DAS, for the maintenance, we need to the live at present to check with a low efficiency. But for the DIS, we can check just on our computer, remote maintenance. Okay, this is for the DAS and DIS. And for the Huawei DIS, with the high view scenarios for the 5G advanced, for the 5.5G, such as enterprise private networks supporting the high precision positioning, for the smart campus with a low latency, less than 5 milliseconds, and for some service like the VR, for the AR, for the VR. And for the DAS, for the traditional distributed system, only address the basic coverage issues and cannot meet 10 gigabit rate requirements of the 5.5G or the needs of the government and the enterprise private networks. Okay. So we suggested the DIS system, the DIS system. Okay, this is for the base station outdoor and indoor. Just some new solutions. And we say beside the device, we also introduced the new spectrum, the new frequency results. Right, this page just show you the results. And we see the release already defined the frequency results to low frequency results and high frequency results. Right, we define FR1 and FR2. And for the different release, for the R15, R16, 17, they define the different frequency bands. And now to the R17, we define the sub-3G, the C-band, and the millimeter wave. Okay. I will type in the chat box. First one is sub-3G. You know the sub-3G, right? That means the frequency below than 3 GHz, right? Lower than the 3 GHz. And for the C-band, just define the frequency band below 3 GHz to 6 GHz. It's like here, the orange area. We say the C-band. And in 5G, in China, we already deploy the C-band in the live network, like the 3.5 GHz. 3.5 GHz. This one. But it has some disadvantages. We say that uplink and downlink decoupling when we use the 3.5, because we see the higher the frequency band, the smaller the coverage area. And also we say the power of the terminal is limited, right? But in the downlink, the power of the base station is sufficient, is enough. So the downlink transmission is not affected. But for the uplink transmission, the power of the terminal is limited. So when UE move to the edge of the cell, when we use a little high frequency band, such as 3.5 GHz, the base station cannot receive the information correctly, right? Cannot receive the uplink information correctly. In this case, we used the decoupling, uplink and downlink decoupling. That means downlink, we still use the 3.5 GHz. But in the uplink, during the uplink transmission, the base station allocates the low frequency band for UE to perform the uplink transmission. So in the uplink, we use 1.8 GHz. 1.8 GHz. 1.8 GHz belongs to the low frequency, right? So when even UE move to the edge of the cell, even the power of terminal is limited, the base station can receive the uplink information, uplink signaling correctly, right? Correctly. Oh, this is a C band, and above 6 GHz, we see the FR2. FR2. FR1 divides sub-3G and C band, and about 6 GHz, we see the FR2. And FR2, especially, we'll talk about the millimeter wave. Millimeter wave is a green part. And the millimeter wave have some advantages and disadvantages. Advantages is we can provide a huge cell bandwidth, right? We see it at most 400 MHz, but for the low frequency band, at most 100 MHz, right? But the disadvantages is we see the higher the frequency band, the larger the penetration loss. So for the millimeter wave, usually for the hotspot scenarios. Now for the hotspot scenarios, HOT, SPOT, for the hotspot. Beside the hotspot, usually we have the millimeter wave base station. It can use to forward the transmission from base station 1 to base station 3. Just forward. Okay, this is for the new spectrum we used in 5G. We used the low frequency band to provide the wide coverage for the broadcasting, and deploy the C-band, deploy the millimeter wave for to improve the system capacity. And we can use the millimeter wave for the hotspot scenarios, and it is more suitable for the massive MIMO, to improve the system throughput, to improve the dedicated UE experience. Why here we see the two advantages? One is for the sales throughput, one is for the dedicated UE. These two are different because for the multiplexing, for the MIMO, for the massive MIMO, we have two schemes. One is SU MIMO, another is MU MIMO. Do you know what's the difference between SU MIMO and MU MIMO? Which one brings the advantages for signal UE? Which one for the wholesale throughput? You can guess? SU MIMO and MU MIMO. Which one to signal UE? Which one to sales throughput? SU to which one? First. Yes, SU to signal user. Yes, to the signal user. What's the meaning of the SU MIMO? Means for one UE during the performed the uplink transmission, they can use the two separate time and frequency results to transmit at the same time. Use the two results to transmit the same messages, right? In this case, we improved the peak data rate of the UE, right? And for the MU MIMO, we said after UE paired, we can allocate the same time frequency results for multiple UE to transmit at the same time, right? So for the wholesale, the limited results are allocated for more UE to transmit, so it can improve the system throughput, right? System throughput. So SU MIMO is for the signal UE to improve the peak data rate, and MU MIMO for the wholesale, for the system capacity, And here, right, the maximum cell bandwidth, right? For the 5G FR1, the frequency band lower than 6 GHz is reach up to 100 MHz. Millimeter wave is 400 MHz, and 4G at most 20 MHz. Okay, this is all the conceptions for the architecture evolution. Then for the network technologies, we introduced in 5G. First one is radio signal propagation. We say when we say the millimeter wave deployment, we say the higher the frequency band, the higher the penetration loss, right? So here we can use the signal propagation to compensate the penetration loss. We know in the actual radio environment, the radio signal sent from the base station to UE is generally blocked by various things like the high-rise building, like the trees, like the rivers. Rather than direct transmission in a line of sight, radio signals in most cases need to be penetrate the obstacles or the reflect or the diffract. And in addition, various types of the interference may occur in the system, right? The interference occurs in the system. For example, the intra-red, intra-frequency interference, or maybe the inter-red secondary harmonic interference, or the external interference, such as from the TV tower and the high voltage power, right? So before a signal is transmitted, corresponding processing needs to be performed, right? Like the channel coding, like the frequency split and the scrambling. This need to be performed to improve the reliability and the spectral efficiency. And here show you the different communication mode. It's communication mode. And here I have some basic functions: source encoding, the channel encoding, the spreading, the scrambling, modulation, transmit, and the receive. First of all, the resource encoding. It still converts the information like the voice and such as a voice. This information needs to be transmitted into the digital signal. So the source encoding is the function of source encoding is implemented by the terminal, and the channel encoding. Channel encoding will improve the anti-interference capability of signals by adding the redundancy codes and check codes to the source data. Then for the spreading, the communication technology that spreads the spectrum of a transmitted signal to the wider bandwidth than the original bandwidth. So after spreading, after the modulation, the signal transmission bandwidth should be much greater than that of the original signal, right? That's why we do the spreading, while we do the modulation. And the transmit end will use the unique code, which is irrelevant to the data transmission, and the receive end must use the unique code for the spreading to obtain the data from the transmit end. Then for the scrambling, in the intra-frequency networking, scrambling codes are used to distinguish the cell to reduce the inter-cell interference. Just to repeat, Control C, Control V. And for the modulation, modulation is a technology that transmits baseband signals to the RF channels, and it is the first choice for broadband access to the wireless interface. The last is transmit and receive, right? RF signals transmitted and received on antenna, and spreading and the scrambling after the spreading and scrambling and the modulation. Okay. And here we need to remember, spreading and the scrambling are proposed in 3G, and the spreading is specific to 3G. Okay, spreading is specific to 3G, not to 2G, not to 4G, not to 5G, only to 3G. Only to 3G. And 4G, we introduced a new one. This one, the orange one, OFDMA. 4G introduced the OFDMA. Consists of the OFDM and the FDMA. Okay, I'll type in the chat box. OFDMA. 4G introduced the OFDMA. And 5G, we evolved, used the FOFDMA. FOFDMA. As before, we say in 5G, 4G and 5G, we have two duplex mode, right? One is FDD, one is TDD. And we said in 5G for the data transmission, TDD is more popular than FDD, right? So we need to talk about the advantages and disadvantages. Why TDD is more popular than FDD? First of all, the FDD. FDD advantages is simple implementation because they use the two separate frequency bands with the same size, with the same frequency size. But the disadvantages is lower spectrum efficiency. Why? Because cannot reuse the same frequency resource, right? And for the TDD, in TDD system, we say uplink and downlink use the different slots and usually share the same frequency, right? And the time division multiplexing technology is used to separate the transmit and the receive signals. Also, we support the dynamic TDD. With the dynamic TDD, the time domain resource can be dynamically allocated and reallocated between the uplink and downlink. For example, 5G. 5G introduced a flexible slot to further improve resource efficiency, adapt to different service requirements, and improve flexibility. Also, 5G introduced technologies like decoupling, uplink and downlink decoupling, like the super uplink. These technologies to resolve the problem of unbalanced uplink and downlink coverage in the high frequency band. After these technologies are introduced, the uplink and downlink duplex mode of the UE can be switched between the TDD and FDD. Right? I'll show you the picture, right? FDD, TDD. For the FDD, the same time, but two different separate uplink results and downlink results. But for the TDD, we use a different time to distinguish the uplink and downlink, but they share the same frequency results. For TDD becoming the mainstream, as we said before, right? We already introduced advantages of the TDD, Okay, the next page is for the multi-access. When we introduce a different rate of 2G, 3G, 4G, we say this for multi-access, right? FDMA, CDMA, TDMA, and SDMA. Right. First of all, the FDMA is the frequency division multiple access. So FDMA is a data communication technology, divides a frequency band into multiple channels for user with a different address to use the different carriers, different channels to implement the multiple access. And for the TDMA, TDMA is a time division multiple access. So it is a communication technique where carriers with the same frequency are divided into several different slots in the time domain, so that user with the different address can use the different slot to implement multiple access. This is TDMA. And for the CDMA, CDMA is a code division multiple access. This technology uses the spectrum spread to form the different code sequence. Then UE with the different address can use the different code sequence for multiple access, different code sequence. Last one, the SDMA for the space division multiple access. The communication mode in which each Earth station use a different spot beam transmitted by the communication satellites, or use the spot beam sweeping to achieve multiple access. So we support this for multiple access. Okay. Here I show you the multiple access. We see the TDMA, FDMA, right? We need to allocate different frequency time results and time domain results. So how to obtain these results? Here, give you the example. It's like a ticket, right? When you take the train, after we obtain the train ticket, we need to find some information to find our seat, right? The train number, the source, and the destination, the carriage, the seat number, right? It's similar to the ticket. In the radio network, we also need to allocate the frame number, the radio frame number, the subframe number, the slot number. Especially in 5G, we have the symbol number. Use this full number to determine which results are allocated for UE, perform uplink transmission, for downlink reception. Okay. This is a time domain results. Radio frame, subframe, time slot, and symbol. Then for the frequency domain, will also define some resource units like the RB, like the RE. RB full name is resource block. It's here. Here is the RB. RB, the protocol already defined the RB size in the time domain is 1 symbol. In the frequency domain is 12 RE. 12 RE. RE is the minimum unit in the frequency domain resource. Frequency resource. Minimum domain unit. Minimum units. RE resource element. RB contains 12 RE. Contains 12 RE. But these two units are used for the data traffic transmission. But for the controls information, for the control signaling, we have another concept. We say the CCE. We say the CCE. The protocol defined the CCE for the control signaling transmission. For the control signaling. Besides the RB, RE, we have the CCE. And the CCE, we can allocate a different aggregation level. In 5G, the maximum aggregation level is 16. That means at most 16 CCE integrated together to transmit one message. Okay, then for the antenna, here just the three new conception. The half wave dipole and half power angle and polarization. For the half wave dipole here, it is composed of two conductors, each with a length of 1/4 wavelength, and the total length is around half a wavelength. And the current is maxima at the center and minima at the ends. But the voltage distribution is opposite for the voltage distribution. Minima at the center and maxima at the ends. Therefore, the half power angle, it's the angle at which the radiation intensity in the antenna's radiation field drops to half of its maxima value. That is -3 dB. And the half power angle, this parameter is an important indicator for measuring the directivity of the antenna. The smaller half power angle indicates the stronger directivity and the more concentrated energy. But the larger angle can result in a wider coverage area. And for the polarization, especially in the line network, we used these two types, vertical and horizontal, and the tilt -+45 degree, these two. But we suggested the second one. The tilt with the tilt 45 degree. The tilt 45 degree. Okay, then also for the antenna, more antenna and beams. This belongs to related to the channel, right? The number of channels, number of beams, and the MIMO technologies. We say that we have the SISO, SIMO, MISO, and MIMO. SISO is very easy to understand, right? Signal input, signal output. So there's no diversity, no transmit diversity, no receive diversity. But when we used the SIMO and MISO, we can receive the diversity. And to 4G, we support the MIMO, right? 40/4R, 40RX, support the MIMO. And we say in 4G, the terminal is 1T2R, at most 1T4R, right? Usually it's 1T2R. So the maximum number of beams, maximum number of channels is limited by the terminal side, right? By the terminal side, because the base station side is 8 TRX, 8 transmitter at receiver, but the terminal side is 1 transmitter to receiver. So it's limited by the terminal. The same in 5G. 5G base station maximum number is 64 TRX. 64 TRX. And we see the maximum number of layers in the live network is 16 layers. Is 16 layers. And for the terminal is 2T4R. 2T4R, 2 transmitter, 4 receiver. So the maximum transmitter channel, the maximum transmitter channel is 4, right? It's 4, limited by the terminal. So we can complete a new kit technology. We say the 3D beamforming. In 4G, we have the 2D beamforming, right? But in 5G, we improved from 2D to 3D, 3D beamforming. AMFORMING, beamforming. What's the 3D beamforming? We will introduce later. Both vertical and horizontal. Both vertical and horizontal will perform the beamforming. And in the live network in China, at most 4 floors, 4 floors for the high-rise building can perform the coverage at the same time. 4 floors, 4 layers. Okay, this is for the antenna. Improve the number of antenna, improve the number of beams, increase the transmit channels. And here we can check the massive MIMO, right? Massive MIMO, we said before, SU MIMO and MU MIMO. Here, this is a MU MIMO, right? MU MIMO. Okay, then for the antenna types, changes multi-frequency, multi-rate, multi-intelligent, just the type of the antenna used to meet the requirements of the different scenarios. We will employ various forms of the antennas and classified into outdoor antenna and indoor distributed antenna based on the coverage area for outdoor or for indoor. Also, we have the omnidirectional antenna and directional antenna. This is based on the coverage direction. Also based on the supported frequency band, we have the signal band antenna and the multi-band antenna. This is based on the supported frequency band. And the antenna type is determined by the service scenario requirements, such as the residential areas and the highways, and the engineering or planning optimization requirements. And with more frequency and higher requirement for the system capacity, the forms and technologies of the antenna become increasingly complex. So here gives the brief introduction to the typical antenna forms. The omnidirectional antenna. For the first one, the omnidirectional antenna is used for the 2G, for the GSM. The early GSM used this type antenna, which have the same radiation power in all directions and support to receive space diversity. And the second, the directional antenna. It's a common outdoor macro base station. Usually have 3 sectors, right? In our live network, in each base station, we need to install 3 directional antenna for the 3 sectors, right? And each sector need to cover only partial coverage areas, and we use the directional antenna in each sector, right? And the third, the dual polarized antenna. With the increase of antenna dipoles, the size of the signal antenna increase gradually. So polarized antenna emerge. And the polarization technology can directly reduce the antenna size. We suggest the tilt 45 degree, right? We see before. And it can reduce the windward side. And the third is the remote RET antenna. The RET antenna. On the live network, after the antenna is installed, its coverage may be ideal, So the tower worker need to climb the tower and manually adjust the down tilt, right? Manually adjust the down tilt. So to improve the maintenance efficiency, we deploy the RET antenna to provide the better coverage than the mechanical adjustment. Generally, the RET antenna have the RET motor. It can be used to remotely adjust the down tilt of the antenna on the MS side. So more easier, the maintenance is more easier than the common antenna, right? Than the mechanical antenna. And then for the multi-band antenna, with the deployment of the communications technologies, the system bandwidth is increasingly large, right? And the required spectrum is much wider. And a multi-band antenna can support the multiple frequency bands or even multiple systems. That means different rates, which can solve the problem of insufficient rooftop resource on the tower. And the multiple antenna and its internal structure are complex. The dipole size and arrangements are also more complex for the multi-band antenna. Then for the MIMO and massive MIMO antenna, MIMO antenna is introduced in the TD-SCDMA system. By using the isolation between antenna array elements. Different beams can be sent in the air to distinguish the different data streams or the different users. For the massive MIMO antenna, on the last page we said we use the 3D beamforming, right? On the 3D beamforming, it is used for the commercial use, introduced for commercial use in the 5G system. And based on the traditional 2D beamforming, massive MIMO adds the vertical beamforming to improve the coverage performance, improve the capacity of the system. This is for the massive MIMO antenna. This page we introduced before, right? Is for the outdoor antennas, right? From 2G to 3G to 4G to 5G. Okay, then for the typical for the features, strong coverage, narrow beams, larger capacity, and more beams. Yeah, for the stronger coverage, what's the meaning of the stronger coverage? We say we perform the beamforming, right? 1G, 2G, we use a wide beam perform the broadcasting. Base station perform the wide beam to perform the broadcasting. So the radius of the cell is limited. It's limited because the power is limited. When we perform the beamforming, especially even the 2D beamforming can increase the cell radius than the 2G, than the 1G. Right. And also we have the 3D beamforming. The terminal 1T to R, we can support the 2D beams, and at most 2 layers, And also we used the tilt 45-degree array, right? So we can obtain the array gain. As we use the 2D beamforming, so we can obtain the beamforming gain. And for the 5G, we see we use the AAU, right? We use the AAU, and the AAU, the maximum number is 64 TRX at the base station side. So we use support the both vertical and horizontal multiplexing, right? So we use the 3D beamforming, and in the line network is 16 beams, and the terminal is 2T4. So the maximum number of layers is 4 during the downlink transmission. Uplink is 2 layers. Also the array gain, beamforming gain, multiplexing gain, diversity gain. All right. Here, just to show you some pictures in the live network, the shape of the antenna of the antenna appearance. Okay, the last part is just to focus on the paging process. Focus on the paging process. Here, show you the ID card. Each of you have the ID card, right? The country will allocate the ID to identify who am I, your name, your gender, your birth, and your live address, and your ID number, right? So it's similar to indicate the country ID, city ID, district ID, community ID, and your location. So how can the core network, how can the base station to find the UE in the radio network? We also very similar, right? We allocate the network ID, the pole ID, location area, seal ID, and the UE ID. Here, what's the meaning of the network ID? What's the meaning of the network ID? Just the PLMN, right? Do you know the PLMN? The public land mobile network, right? And PLMN is combined with MCC and MNC, right? No, not the MSC. MCC and MNC. I see these two. MCC is the country code. MNC is the operator code, the network code. For example, in China, MCC is 460, and MNC is the operator. Maybe for China Mobile, for China Telecom, they use a different number, different value. It is a network ID. And the pole ID, the location area. This is for the LA and the TA. The LA is the location area, and the TA is the tracking area ID, right? We have the TA list, we have the TAC. During the TA list, find the TAC, the TA code. And within each TA, we need to define in which cell, right? Register to camp on which cell. So we need to allocate the cell ID. When UE perform the registration to the core network, perform the cell registration, the cell camping, need to receive the cell ID, receive this information. And cell ID, we use the PCI to indicate, right? The PCI. PCI full name is a physical cell ID, physical cell ID. We have the different value. How can we find the PCI? Is to search the system information, right? Search the system information. During the MIP message, we can receive the PCI. And after we find the PCI, we need to, after you successfully register to the core network, the AMF will allocate the GUTI for the UE. GUTI is used GUTI. This one. GUTI is the identifier allocated by the core network. So after UE perform the deregistration with the core network, not use the GUTI. Right? So we also have the IMSI, right? We have the IMSI. You know the IMSI, right? IMSI is the global unique ID of the UE. Global unique ID of the UE. It's like our ID card, But for the GUTI, is allocated by the AMF, So according to this different identifier, the radio network can know where is the UE. When the downlink data arrived, the core network will perform the paging procedure to find the UE. After you give the response, we need to perform the synchronization of both uplink and downlink. Then UE can receive the downlink data. Okay. So here we use the paging. So paging is just the broadcast the searching information. Here to inform UE, there is a downlink arrived. You need to resume to the connected mode and to receive the downlink message. But in some cases, the paging is not initiated by the AMF. And we said in 5G, we introduce a new status like the inactive status, right? The inactive state. In this case, the core network think UE is in the connected mode, but actually UE is in the inactive. In this case, the base station will perform the paging, in the RNA area. In this one, the RNA area full name is RAN notification area. RAN FICATIONAII. RAN notification area. That means within this RNA area, all base station will perform the raging to search the UE, to inform the UE. The core network already sent the downlink signaling, the downlink data to you. You need to redeem to the connected to receive. Here you can find the network. Here just show you the China code, right? Like China country code. And the pole area, the location area, the COID, the COID. Okay, the level by level paging, location reporting. Level by level paging is I say the normal paging procedure. And for the location reporting, what's the meaning? Because the UE is moved, right? It's mobility, it's moved. So when the UE in the connected mode and find the TA has been changed, the ID has been changed, location ID has been changed, we need to perform the location update procedure to inform the core network. Now I'm already moved to a new coverage area, and you need to storage the ID, the location ID. When the downlink data arrived, you need to find me through this ID, right? Okay, and for the mobility, maybe from Thailand to China, to another country. In this case, we have the condition is international roaming, right? I need to have the roaming. For example, in China, I use China Mobile. When I move to South Korean, they use KT, right? So when the China Mobile app perform the roaming with the KT, when I moved to South Korean, I can use the operator of KT. This is roaming. And after the UE move from Thailand to China, if they complete the roaming, the protocol, they can use the China Mobile, use the China Telecom. Then the UE arrived in Hangzhou airport. It will search the Hangzhou ID, right? The city ID. Then move to Beijing. Needs to perform the location update. To inform the core network. And within Beijing, we have several different districts, right? Haidian, Xicheng. So when you move to different districts, you also need to perform the location updates, right? And within the same core network, we use the same TA. I just need to allocate the LA, right? But when we moved to another TA, we need to perform the TA update. And in each district, they have different cell. When we move from cell A to cell B, we have another procedure. Maybe handover, maybe reselection, right? Maybe handover, maybe reselection. Okay, international roaming, provincial roaming, location updates, and reselection or handover from cell A to cell B. And for the handover, we also support a different type of the handover. Here, handover technologies. One is hard handover. Second is soft handover, and the button handover. For the hard handover, it just means disconnect before connect. First disconnect, then connect to a new base station. So it will interrupt the service and results in around 200 milliseconds of the communication interruption. So it's usually involving in the different frequency base station or the internet scenarios, maybe 2G to 3G to 4G. Advantages is low resource consumption, but easy to call jobs. Then the second, the soft handover. Soft handover means connect before disconnect. Connect before disconnect. So where the MS maintain the connections with both the old and the new base station at the same time until the new link stabilized. So there's no interaction. The disadvantages will consume high resource scheduling, but can reduce the call drop rates. Used in the 3G networks like the CDMA 2000, like the WCDMA, and also for some high-speed mobile scenarios. And the last one is baton handover. It's based on the intelligent antenna positioning technology. The MS forwards the signal through the relay nodes during the handover process to achieve a no disconnection transmission. The characteristic is intermediate between the soft handover and the hard handover, can perform the better resource efficiency than the soft handover. But it depends on the precise distance or the azimuth measurement. Based on the precise measurements, so it will result in the lower handover delay. And usually used for the TD-SCDMA system, and like for the cooperative communication scenarios, like the maritime land cooperative communication scenarios. Okay, just three types, three technical handovers. Hard handover, disconnect first, then connect to a new one. Soft handover, first connected to a new base station, then perform the disconnection with the old base station. And the button is first perform the precise measurements, perform the pre-synchronization to reduce the delay, reduce the interruption delay. Okay, that's all information I want to share with you. Here, just to give you the summary, right? First, large bandwidth, we say in 5G, from 2G to 5G. Until 5G, we already achieved 100 MHz for FR1 and 400 MHz for FR2. Higher rate from 100 gigabits to 5G is 10 gigabits. And the multi-access technology, FDMA, TDMA, CDMA, OFDMA, especially in 5G, we use FOFDMA, right? And high order modulation. Here we not introduce the details of the high order modulation, but especially in 4G, we can use the 1024 cone. But this modulation scheme only used for with the high channel condition, and only used for the data traffic transmission. Right? For the signaling, we also use QPSK because we need to guarantee the transmission accuracy, right? So we use a low order modulation, the QPSK. And for the multi-antenna technology, signal antenna diversity, MIMO is in 5G, we use a massive MIMO. For SU MIMO, MU MIMO, increase the signal UE peak data rate, increase the system throughput, increase the spectrum efficiency, right? Also, the evolve of the site type for the outdoor base station and indoor distributed system, the DAS to DIS, and from the RU-AAU antenna to the BBU and AAU, right? And the key technologies, mobility. We need to perform the paging. The core network perform the paging, base station perform the paging to find the UE. And when you move to another coverage area, need to perform the location update. And the core network, the structure updates, we have the CS to CS plus PS and all IP involved in 4G, and the cloud definition involved in 5G. evolved in fact because we introduced the CUPS. For the AMF, SMF centralized deployed, and for the UPF deployed nearest to the base station site, right? Okay, this is all information I want to share you today. So for this part, do you have any questions? Anyone here? No questions? What's the difference between IMSI and IMEI? Okay, IMEI is the ID for the device. Okay, for the device, maybe for the phone ID. But for the IMSI, it's for the logical ID of the UE. For the ID card, for the UE. When you buy a new smartphone, the IMEI may be changed. But for the Signal UE, the SIM card, the IMSI use the same ID. You know? Wi-Fi G converting too fast, or if the handover reduce latency. Oh, sorry. Please let me check. It's like that. We say, do you know the dual registration? Do you know the dual registration? Perform the registration with two at the same time. In this case, first before the handover, we perform the registration with the base station 1, right? But during the mobility, during the move, the UE want to perform the handover to the base station 2, right? To the base station 2. In this case, we can allocate, we can perform the synchronization with a new base station, with a new cell. And after we complete, we allocate all the results for the UE, and UE perform the registration to the new cell. In this case, UE can can hand over the service to the new base station. In this case, the new base station already performed the service, right? Already support the service and cannot interrupt the service. It can improve the user experience. Under this case, we can disconnect disconnect between the UE and the old base station. Can reduce the latency. Do you know that? So we can we can save the latency for the results preparation for the registration to the new base station. Why is the more sensitive to noise and difference than lower order COM schemes? For the COM and for the low order COM and the high order COM, especially to compare the QPSK and the 256 COM, we say for the QPSK, that means at the same time transmit 2 bits, right? And for the 1024, it means at the same time is 10 bits, right? At 10 bits. So the transmitter size is increased, right? It's increased. And we know during the transmission, we maybe occurs the interference. So during interference, with the large size will be occurred, the rate of the interference is high. So for the higher order modulation scheme, usually used for is more sensitive to the interference, to the noise. But for the QPSK is more how to say that, can improve the efficiency, the transmission efficiency for the signaling. What are the main difference between NSA and SA? Okay, good question. We say the 3GPP has defined the NSA and SA, right? NSA full name is a non-standalone, right? Non-standalone access, and SA is standalone. For the non-standalone, that means the UE can perform the registration with both 4G and 5G, both 4G and 5G. And for the SA, that means whole 4G or whole 5G. 4G base station with 4G core network, or 4G or the 5G base station with 5G core network. But NSA means maybe the 4G base station with both 4G core network and both 5G core network at the same time. And maybe we involved the base station to how do you say that? Evolve the InnoB, or directly use the GNOB. And we can connect it with the 5G core network at the same time, reuse the 4G core network, reuse the 4G core network. This is the NSA. NSA. And for the SA, if we want to evolve from 2G to 4G by the SA, we need to build the whole new base station and build the whole 5G core network. So it will cost, the cost is a little high. It's very high. But for the NSA, maybe we can reuse the 4G results, reuse the 4G base station and 4G core network, then evolve to the 4G, to 5G, to 5G. Page 50. You mean the 5G we choose the hard handover? Here the 5G hard handover. What's the meaning? We say especially in 5G we already deployed the SA 5G, right? The 5G base station and the 5G core network. This right. And we need to, in some cases, we need to perform the voice call, right? We say the EPS fallback. In this case, the UE first needs to initiate the registration to the 5G IMS. After received the reject response, reject response, you need to fall back to the yes.
Sí.
What's problem?
Sí, sí, mira, yo lo que voy a hacer es ella ahorita está contestando, la teacher está contestando las preguntas de los chicos. Y ya estás poniendo nuevamente el QR para la asistencia. Entonces, en cuanto, si tú te puedes checar que ella ya no esté con la camarita abierta, eso significa que ya terminó. Si tú te das cuenta de eso, entonces ya puedes, ¿cómo se llama? Pues darle close.
Speak to me.
¿No? Bueno, ella es Lidia, ¿ok? La teacher es Lidia. Lidia y su user es 25 OWAPE. Está casi después de Héctor Liu, después de mí y después de Héctor en los asistentes. Ella es la teacher. Entonces, cuando tú ves que ella ya no está con su camarita abierta, eso significa que ya dejó de contestar las preguntas.
Or maybe we continue to explain the question. We say in some cases for the 5G, for the voice, right, we perform the EPS fallback. In this case, first need to initiating the 5G core network, then fall back to 4G. In this case, first 5G need to reject. After the reject, you need to suspend the data transmission, then fall back to 4G, perform the voting, right? In this case, we need to disconnect the 5G connection, then perform the registration to the 4G, to the LT, to the 4G IMS. Then we can perform the voting. So in this case, this is a hard handover. This is hard handover. I think the uplink also use the OFDMA. Both uplink and downlink use the OFDMA, the same technology. The trade-off between spectral efficiency and signal robustness in 5G. Of course, we cannot achieve the highest spectral efficiency. We also need to consider the signal robustness. We have the max gain to consider this question. So, we have any other questions? If no, that's all the content about this morning training. Yeah, you're welcome.
Thank you, Lydia. Thank you very much. I'm sorry because I was with my micro opening. Sorry.
It's okay.
Yes.
So, yes, please.
Yes, for the students, just we want to share for 5 minutes more the QR for the attendance, in order that they can register their attendance. Okay. Thank you very much, Lydia. And
All right.
we will see you tomorrow morning. Thank you, everybody.
All right.